Hello, and welcome back to another IB Math speedrun with me, Fitz. And so in this one, we're going to be finishing up chapter 8.4, and we need to talk more about the Maclaurin series and about the binomial expansion. So let's jump right in. So, of course, the Maclaurin series is an infinite series, and so, in the last speedrun, I think we were doing the first 4 terms, but really you can expand it to an infinite amount. So, we have that's pretty obvious, I guess. But what's more important is to note the binomial expansion. So I think we touched briefly on the general binomial expansion. It looks something like 1 plus p to the x plus p times p minus 1 over 2 factorial x squared. This is, of course, for a binomial of 1 plus x to the power of p. And so this is extremely useful for when p is equal to a negative value. So it means we can't just expand it. So this is the general binomial expansion. And so yeah, this is very useful, and we'll go through some questions, but it's also worth noting some other expansions. So that was the binomial one, where we have the sum from n is 0 to infinity of p times p minus 1 times p minus 2, and so on until p minus n plus 1 all over n factorial times x to the n. So this is the binomial, but let's look at some other ones, some other Maclaurin series. So the first one is e to the x, which is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on, which is equal to the sum between n equals 0 and infinity of x to the n over n factorial. Next, the sine series is equal to x. I think we covered this one in the last video. X minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. So this is equal to the sum between n is 0 and infinity of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial. As you can see, alternating between positive and negative. Similarly, cosine just starts off the cycle at a different point. So we have cosine x is equal to 1 minus x squared over 2 plus x to the 4 over 4 minus x to the 6 over 6, and so on. And so this is equal to the sum between n equals 0 and infinity of negative 1 to the n, again, times x to the 2n over 2n factorial. Okay, so next we want to note 2 more notable ones, which is ln of 1 plus x. 1 plus x is equal to x minus x squared over 2 plus x cubed over 3, and so on. And it's the sum between n equals 0 and infinity of x to the n over n. It might be being multiplied by minus 1. That's a bit weird. Anyways, finally we have arctan x is equal to x minus x cubed over 3 plus x to the 5 over 5, and so on. So it's like the opposite. No, it's actually relatively the same as sine x. Interesting. So we can approximate it as n equals 0 to infinity of negative 1 to the n over x to the 2n plus 1 over 2n plus 1 factorial. That's interesting. That means it's the same as the sine graph, which is weird. Maybe the book's made an error? Let's just check. So we have sine x, and we have arctan x. So I guess the starting part is roughly similar. If we plug in x minus... Oh, that's why. It's missing the factorials at the bottom. So this is just x cubed over 3, so this is no longer a factorial. And the same for this. Note that it's not a factorial either. So, with that being said, let us jump into some questions. So, I'll do the even ones. So, actually, I'll do the odd ones. So first we need to find the Maclaurin series for the following functions. And the first one is y is equal to e to the 3x. So, this is, of course, f of 0. F of x is equal to this. So f of 0 is equal to 1. F prime of x is equal to 3 e to the 3x. So f prime of 0 is equal to 3. F double prime of x is equal to 9 e to the 3x. So f double prime of 0 is equal to 9. And so we can see that this is going to follow the sum of, where is it? 1 plus 3x over 1 factorial plus 9x squared over 2 factorial and so on. And so we can write an approximation of this as the function from, let's say, I think it's n is equal to 0 to infinity of 3 to the power of n over n factorial times x to the n. So that looks like a pretty good approximation. Okay, next one. We have f of x is equal to 1 over 1 plus 2x. So, or 1 plus 2x to the minus 1. To the minus 1. So f of 0 is of course equal to 1. So f prime of x is equal to minus 2 times 1 plus 2x to the minus 2. So f of 0 will be equal to minus 2, since this part will always be equal to 1. Next we have f double prime of x is equal to 8 times 1 plus 2x to the negative 3. So f double prime of x of 0 is equal to 8. And then next we have f triple prime of x is equal to negative 48 times 1 plus 2x to the negative 4. So f triple prime of x will be equal to negative 48. So as we can see, we have some sort of alternating series. So 1, 2, 8, negative 48. So that's 6. Okay. So our series will look something like this. We have 1 minus 2x plus 4x squared minus 8x cubed. So this is simply equal to the sum from n is equal to 0 to infinity of negative 1 to the n times 2, or actually this is just negative 2 to the n. Just remove that, negative 2 to the n times x to the n. So yeah, that was pretty good. And then let's look at one of the final series we have, and that one is y is equal to sine squared x. So of course f of 0 is equal to 0. Now let's get f prime, which is we can rewrite sine squared x as sine x squared. And so this is equal to 2 sine x cosine x, which we can also rewrite as sine 2x. So f of 0 will still be equal to 0. So next we have f double prime of x is equal to 2 cosine 2x. So f double prime of 0 is equal to, I think it's just 2. And then f triple prime of x will be equal to, of course, negative 4 sine 2x. So this will be equal to 0, and then we'll have negative 8, and then so on. So our series looks something like x squared minus 8 over 4 factorial x to the 4 plus 32 over 6 factorial x to the 6. So we can write this, I think, as, what would be the best way to write this? Oh, okay, I mean, you can utilize the trick of the odd numbers. So we have n equals 0 to infinity, or alternating negative, so this would be negative 1 to the n, and then we would have to the power of 2, so 2 to the power of 2n plus 1, 2n minus 1 to make it odd, times x to the 2n, all over, and 2n factorial. Yeah. Nice. So that was that. Okay. Next question is use a partial fraction to decomposition to express f of x. Okay, so this is a common question. Is equal to 7x minus 2 over x plus 1 times x minus 2 as the sum of two rational functions, and find the Maclaurin series. Okay. So we need to use partial fraction decomposition. So we know that 7x minus 2 is equal to a times x minus 2 plus b times x plus 1. So 7 is equal to a plus b, and negative 2 is equal to negative 2a plus b. So 7 is equal to 3a minus 2, a is equal to 3, b is equal to 4. Yeah. So we have this is also equal to 3 over x plus 1 plus 4 over x minus 2. So now that we've decomposed this, we can expand this as a binomial, and we often have to do this. So this will be equal to 3 times x plus 1 to the minus 1 plus 4 times x minus 2 to the minus 1. Well, the question is, what does this evaluate into? Do we have to get the sum? Yeah, we have to get the sum. Okay. So we know the binomial series sum, when we have, well, we want to rearrange this into a form 1 plus x. So this will be equal to 3 times 1 plus x. 1 plus x, and then in this case we have to say this is equal to minus 4. Oh, actually, let's just transform it using the fraction, might look easier. So this is minus 4 over 2 minus x. So this is minus 2 over 1 minus x over 2. So this is equal to 3 times 1 plus x to the minus 1 minus 2 times 1 minus x over 2 to the minus 1. We need to ensure this term is equal to 1 so we can use it in a binomial expansion. And so finally, we can rewrite these binomials as sums. So we have 3 times the sum of, what is this, p, we have negative 1 times negative 2 times negative 2 minus n, or is this like dot dot dot, all over n factorial times x to the n plus minus 2 times the sum of actually, wait, this will just be negative 1. What am I doing? because we will just be alternating since we start at -1. So this will be equal to 3 times the sum from, please stop lagging, n is equal to 0 to infinity of -1 to the n times x to the n minus 2 times the sum from n equal to 0 to infinity of 1 over x minus x over 2. Well, this is minus, so this will cancel out. So it looks like it's just x over 2 to the n. Yeah. So if we combine this into a single sum, I guess this will look a bit neater. So n is equal to 0 to infinity of 3 times -1 to the n times x to the n minus 2 times x over 2 to the n. Yeah, so this would be our answer. Nice. Okay, on to the next question. And the next question is, we need to find the following limits using Maclaurin series. So the first one is the limit as x tends to 0 of e to the x minus e to the negative x over x. Well, we know that e to the x is equal to, this is equal to the sum from n is equal to 0 to infinity of x to the n over n factorial. And then e to the negative x, well, what would that look like? This would just be the sum from n is equal to 0 to infinity of -1 to the n times x to the n over n factorial. And so we can combine these two sums into one Maclaurin sum. So what would this tend to be? This would tend to be equal to the limit as x tends to 0 of the sum of n equals 0 to infinity of alternating odd and even ones. Because when n is even, it doesn't exist. So it's only when n is odd does the sum exist. So this would be equal to x to the 2n plus 1 over 2n plus 1 factorial. And what do we know that this is equal to? Sorry about that. And so how do we get, actually sorry, I made a little mistake here first of all, because when we add both terms, it's equal to 2 times the sum. And so how do we approximate this side? Well, if you notice, this side was actually, well, we can recognize this because sine x can be approximated as the sum of from infinity n equals 0 of -1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. So we can then approximate this function as the absolute value of sine x. So this will be equal to the absolute value of 2 times the absolute value of sine x over x, And if you notice, first of all, we still can't solve this, so we can use L'Hopital's rule, because as x tends to 0, this will tend to 0 over 0. So we can get the derivative, so this will be equal to the limit as x tends to 0 of 2 cosine x over 1. And as x tends to 0, this will tend to 2. So that is the answer. Okay, next one, we need to do the limit as x tends to 0 of x squared minus sine squared x all over x squared times sine squared x. Interesting. Okay. We need to first get the Maclaurin series, I guess, for sine squared x. So this would be equal to f of x is equal to sine squared x. I think we did this one already actually, so this should be equal to 0. F prime is equal to sine 2x. Oh, so this is the one where this is the sum. This is the sum of -1 to the n plus 1. Nope. Times 2 to the 2n minus 1 times x to the 2n all over 2n factorial. So if we're subtracting this from x squared, I think it just means we're skipping the first term. So oh, okay, that's interesting actually. So if we're subtracting this from x squared, this is equal to effectively the sum between -1 to the n times 2 to the 2n plus 1, since we're skipping the first term, which is 1, times x to the 2n all over 2n factorial. It might be 2n plus 2 factorial. I think it's 2n plus 2 factorial. So more or less the top part, as x tends to 0, is equal to 1/8. No, it's equal to 8 over 8 over 4 factorial times x to the 4 minus 32 over 6 factorial times x to the 6 plus 128 over 8 factorial times x to the 8, and so on. And this is being divided by sine x squared, which is, we can expand into that, times 2x. So this is actually being divided by 2x squared times x squared to x to the 4 minus 32 over 6 factorial, sorry, minus 8 over 4 factorial x to the 6 plus 32 over 6 factorial x to the 8 minus 128 over 8 factorial x to the 10, and so on. We can divide all the terms, sorry, I'm back. What we can do here is we can divide all the terms by x to the 4. So that leaves us with the limit, as x tends to 0, of 8 over 4 factorial minus 32 over 6 factorial times x squared, and so on, over 1 minus 8 over 4 factorial x to the 4, and so, x squared. And so more or less, all of these terms with x squared and beyond, as x tends to 0, will just equal 0. So this resulting fraction will equal 8 over 4 factorial, which is equal to 8 over 24, which is equal to 1/3. So that's how you solve that problem. Nice. Sorry, I just had to plug in my charger, so let's clean up the last few questions here. So the fifth one is use the binomial series to find the Maclaurin series for f of x is equal to 1 over 1 plus x cubed, which is of course equal to 1 plus x to the -3. So how can we find a binomial series for this? Well, this will be equal to 1 plus 1 minus 3x if we expand it binomially, plus -3 times -4 over 2 factorial x squared plus -3 times -4 times -5 over 3 factorial x cubed, and so on. So Let's see what we can evaluate this to. This looks like 1 minus 3x plus 6x squared minus 10x cubed. Yeah. And so this looks sort of like the triangle number series. So anyways, this is 3, of course, this being a gap of 2, this being a gap of... no. Triangle numbers is n times n plus 1 divided by 2? Oh my gosh, why can't I remember triangle numbers? Yeah, 2 times 3 over 2, 3. 3 times 4 over 2, 6. Okay, so this is correct. So this is the triangle numbers. And then we have to have negative 1 to the n times n plus 1 over 2 times x to the n. The sum from which n is equal to 0 to infinity looks about right. So, yeah. So, hold on, n equals 0. Actually, this is n plus 1 times n plus 2. So this here should be n plus 2. So yeah, so this is the series. And then the next one is we need to find an expansion for 1. I'll just write it in power form. It's equal to 1 plus 2x cubed to the negative 1/4. So if we expand this binomially, we have 1 minus 1/4 times 2x cubed plus 1/4 times negative 5 over 4 over 2 factorial times 2x cubed squared. And so let's evaluate these first few terms. This is 1 minus 1/2 x cubed plus this is equal to 5 over 2, 5 over 8 x to the 6. Yeah. And so this should be equal to the sum of from n equal to 0 to infinity of course, negative 1 to the power of n. And then what can we do here? This is 1, 5, and then we'll go 9. So times 4n minus 3 over 2 to the power of n times n factorial. Because what's the next term? Let's actually do the next term. So we have plus negative 1/4 times negative 5 over 4 times negative 9 over 4 all over 3 factorial times 2x cubed cubed. So this is negative, where's my calculator? Calculator, oh, it's here. Wait, what am I doing? Sorry. So we have negative 5 times 9 divided by 6. So we have, oh, so it's actually the odd numbers being summed up here. So it's not just 4n minus 3, which is what I thought. So it's actually 1 times 5 times 9 all the way to times 4n minus 3 over 2n n factorial, of course, times x to the 3n. So yeah, that should be the answer. And then let's move on to the final 2 problems. So first, find the first 3 terms of a Maclaurin series. The approximate solution to the derivative of y is equal to negative minus y tan x is equal to cosine x if y of 0 is equal to pi over 2. First 3 terms. Okay, first 3 terms. And so we have y of 0 is equal to 1. And we have y prime is equal to cosine x plus y tan x. So y of 0 is equal to, y of 0 is equal to pi over 2. Y of 0 here, that's 1. That's just 1. Then y double prime is equal to derivative of this is negative sine x. And then derivative of this is product rule. This would be plus secant squared x y. So y secant squared x plus y prime tangent x. So secant squared x is equal to 1. So this would be equal to, secant squared x 1 over cosine 0 is equal to 1. So this is equal to negative. It's equal to negative sine of 0, which is 0. And then tan 0 is 0, so it's just y. Oh, negative pi over 2. Ooh, okay, wait. Oh, okay, so y of 0 is equal to negative pi over 2, and then y of 0 here, y double prime of 0 is equal to y, which is equal to negative pi over 2 anyway. So, because, so negative pi over 2. So the Maclaurin approximation for this is equal to negative pi over 2 plus 1 times x minus pi over 2, so it's minus pi over 4 x squared. So this is the approximation. Finally, use Maclaurin series to show that if the solution of the initial value problem y prime is equal to y squared plus 1 and y of 0 is equal to 0, then y equals tan x. Okay, let's look. So y prime of 0 is equal to 1. Y double prime is equal to 2y prime. So y of double prime of 0 is equal to 2. It's equal to 0 because y of 0 is 0. Y of triple prime is equal to 2y prime squared plus 2y, is that correct? Yeah, that looks correct, at least to me. So y triple prime of 0 is equal to 2y, so it's equal to 2. So what we're saying is the series is equal to 1 plus, 0, is this equal to x plus 2 over 3 factorial, so this is 1/3 x cubed. Oh, and of course, okay, so because this is x plus 1/3 x cubed, but that's plus, I assume it continues 1/5 x to the 5. This series should actually be equal to tan of x. Let's just check. What is the Maclaurin series for tan of x? So y is equal to tan x. Then y prime is equal to secant squared x. So y of 0 is of course equal to 0. Y of 0 is equal to 1. Y double prime is equal to, well, secant squared x is 1 plus tan squared x. So y double prime is 1 plus tan squared x. So this will be equal to secant squared x tan x, 2 secant squared x tangent x. So y of 0 is of course equal to 0. And then if we get the next derivative, y triple prime, this will be equal to 2 times 1 plus tan squared x. So this is 2 times tan, 2 tan x plus 2 tan cubed x. So y triple prime of 0 is equal to, the derivative of this. So that's equal to 2 secant squared x plus 2 secant squared x tangent squared x. No, 6 secant squared x tangent squared x actually. It should be equal to 2, right? Oh, we got 4 over here? No, we actually got 2. Okay, so this is 1, 0, 2. And as you can see, this expansion also goes 1, 0, 2. So this is, in fact, the Maclaurin expansion for tangent of x. So that was all for today's speedrun. I hope you enjoyed this, and I hope to see you in the next one where we'll be doing the chapter review. See you then.